Okay, this is video 2 of our second lesson in the acid-base series, okay? And we're going to stick with our theme in terms of working through what happens with the Davenport diagram in terms of buffering, but now we're going to add an extra complication. We're going to make this a case of respiratory acidosis. You know, the last video we did metabolic acidosis in the form of an added non-carbonic acid like lactate. Okay, like lactic acid, excuse me. Now we're going to do a respiratory acidosis. So respiratory acidosis takes place when your PCO2 goes up. So let's say you've got some sort of abnormality in respiratory function. That abnormality is causing your, the ability of your lungs to exchange gases to go down, and therefore your partial pressure of carbon dioxide in your blood rises. Okay, so let's talk it through just like we did with our metabolic acidosis. The first thing you'll notice is that our carbon dioxide will no longer reside on our 40 millimolar of mercury carbon dioxide isobar because our PCO2 is going up in a respiratory acidosis. So that's the first thing that's going to happen on our Davenport diagram, all right? Now let's talk through the rest of this. My carbon dioxide has gone up, okay? That shifts my carbonic acid equation to the right. That increases hydrogen ion concentration, okay? So some of those hydrogen ions, the vast majority of them, will be bound to buffers, and the major buffer is hemoglobin. So I have Hb for hemoglobin here. Hemoglobin binds hydrogen ions and becomes hydrogen ions bound to hemoglobin, okay? Notice that as we shift this equation to the right, we also increase bicarbonate. So with our metabolic acidosis, without a respiratory compensation yet, we only changed bicarb. Now we're changing both carbon dioxide and bicarb because this equation is shifting and because both are going up now, all right? So this won't be as simple as the last example was, all right? So the question we have to ask ourselves is how much, okay? We know we've increased the carbon dioxide. If we increase the carbon dioxide, how much will bicarbonate go up? Well, we get a bicarb made for every hydrogen ion that's made. And the majority of those hydrogen ions that are made are going to be bound to hemoglobin. Free ion concentration only goes up a little bit, okay, because we know that we're buffering the majority of our hydrogen ions, okay? We're producing a lot, but the free concentration only goes up because buffers like hemoglobin are sopping up the extra hydrogen ions. So how much of this goes up depends upon how much hemoglobin binds to the hydrogen ions. Okay, so that's so the real question is how much hydrogen ion is binding hemoglobin. Okay, and that will tell you how much bicarb you're producing. So the answer to that is for every change of 1 pH unit, you get a change of 11 millimolar bicarbonate. So I raise my carbon dioxide. If I raise it a lot, enough to drop the pH by 1 unit, that means that enough hydrogen ions will be bound to hemoglobin to produce 11 millimolar bicarbonate. So for a respiratory acidosis, you know that as your carbon dioxide goes up, you can figure your bicarb will go up 11 millimolar for every pH unit you drop, okay? And that's because that's how much hydrogen ion is binding to hemoglobin here, okay? So another way of saying that is that on your Davenport nomogram, as you move from carbon dioxide to carbon dioxide isobar, you move up this green line, up and down this green line, and that green line has a slope of 11, which means that as my carbon dioxide let's say I have hypoventilation, okay, or a respiratory acidosis, okay, because we're increasing CO2. But now we increase CO2 going from isobar to isobar, and as we do that, we know we're also increasing bicarbonate. So we don't just go straight across, we go up this green line so that we're producing bicarbonate here as we increase our carbon dioxide here. So we go along the green line and we produce bicarbonate at the same time we're moving to our next isobar. Okay? So a respiratory acidosis or hypoventilation would cause your bicarb to go up and your CO2 to go up, and they would both go up such that they went along this green line, which has a slope of 11. Okay? All right. What about hyperventilation? Let's say we increase our respiratory rate. Well, now we're going along the green line, but now we're blowing off CO2, so our partial pressure of CO2 goes down, and we're moving from 40 to 30 to 20. And we're doing that along the green line, so that now we are consuming bicarbonate. At the same time, our pH goes up, and our carbon dioxide goes down. So now imagine the carbonic anhydrase equation. We're here, CO2 drops, we pull our equation to the left, and bicarb is consumed as you do that, okay? As you produce more water and carbon dioxide. So the bicarb goes down, and the hydrogen ions are dropping as we shift to the left. The pH goes up, and as the CO2 goes down, okay? All right. So whenever the CO2 changes, you go from isobar to isobar, but you do it along this green line or a line that is parallel to that green line. For instance, what if I'm here where I've got, let's say 18 millimolar bicarb, and let's say our pH is about 7.15, somewhere in that area, okay? And now, let's say you increase your respiratory rate so that you can get rid of carbon dioxide. You might want to do that because you might want to raise the pH back toward normal, okay? If you increase respiration rate and you blow off carbon dioxide, you're going to move from this X to isobars with lower carbon dioxides, okay? And you're going to do that along a line that's parallel to this green line, okay? So as you reduce carbon dioxide, you also reduce bicarb. I know that this slope is supposed to be parallel to the green line. I can't draw it soon. Okay, but it's parallel to the green line, and as you drop carbon dioxide, you are actually dropping bicarb as your pH goes up toward normal. Okay, so you move from that X along the line parallel to the green line, down from isobar to isobar, from carbon dioxide to carbon dioxide as you blow off more and more of it. All right? All right. So let's look at our two types of acidosis and what they look like on our Davenport nomogram. So here we have increased non-carbonic acid. Let's say this is a metabolic acidosis. Let's say it's lactic acid, okay? Produced by your muscles or your tissues when you have hypoxia, okay? And this increased PCO2 could be due to a respiratory problem where you're having a problem with gas exchange. So this would be respiratory acidosis. This would be metabolic acidosis. So what happens to pH? Well, if we increase non-carbonic acid, we're adding hydrogen ions to that, and our pH goes down. And you can see that here. Here's our Davenport nomogram. We're going down in pH along our 40 isobar, assuming that we've got a normal PCO2, which we should. We can safely assume. And so our pH goes down along that green line, okay? So we get a decrease in pH. We also get, let's take a look at our respiratory acidosis. Increased CO2, we go isobar to isobar, we start at 40, we go up because our CO2 is rising because of our respiratory problem. And as we go up from isobar to isobar along our green line, our pH drops. So we get a decrease in pH with an increased carbon dioxide and respiratory acidosis. Let's look at our bicarb. With a metabolic acidosis, like lactic acidosis, our bicarb actually goes down. And the reason is because we've increased hydrogen ion concentration. Those hydrogen ions are combining with bicarb, and our carbonic acid equation is being shifted to the left. And as that combination takes place, and we produce CO2 and water, our bicarb decreases. So we get a decrease in bicarbonate. With our metabolic acidosis, our increase in non-carbonic acid, okay? And you can see that here on the Davenport, we're going down along our 40 isobar, pH is dropping, and our bicarb is dropping right along with it, okay? Decrease, decrease. For respiratory acidosis, CO2 is going up, and that is shoving our carbonic anhydrase equation to the right. We're producing more hydrogen ions, our pH is dropping, we already said that, but we're also producing more bicarb when we do that. So now, as we go from isobar to isobar with our increased CO2, we go up along our green line and we're producing bicarbonate. So our bicarb goes up with our respiratory acidosis, it goes down with our metabolic acidosis, our increase in non-carbonic acid. Okay? All right. And you can see that. All right. How about PCO2? For our metabolic, with no respiratory compensation yet, no change. Okay? Because your partial pressure of carbon dioxide in your plasma equilibrates with the alveoli, which are hooked up to the atmosphere, which is just like an infinite sink for carbon dioxide. So you can produce more through your carbonic anhydrase equation. It's just dissipated in the atmosphere. You stay at 40 millimolar of mercury PCO2. So here we have no change in CO2. We're just going down along our 40 isobar for our metabolic acidosis. And for our respiratory acidosis, we're obviously increasing CO2. That's what's causing our acidosis. So CO2 is going up, and we're going from isobar to isobar along the green line. All right? All right. So, to wrap it up with some rules for buffering in the face of acid-base imbalances. First of all, notice that buffering decreases the magnitude of the pH change. It does not prevent pH changes. Nothing we did in this video actually prevented a change in pH. It decreased the magnitude of that change, but it didn't prevent it, all right? Your non-carbonic acids are buffered by all systems. So you add non-carbonic acid, you're going to get hydrogen ions. The added hydrogen ions are going to bind to bicarb, which is a carbonic acid buffer. Okay? And they're also going to bind to any non-carbonic acids that are available in the body for them to bind to, like hemoglobin, okay? Which is the big one. If it's a carbonic acid that's being buffered, let's say because you've increased CO2, okay? Now that is only buffered by non-carbonic acid buffers, that is, buffers like hemoglobin. In fact, when you add CO2 and you produce an acidosis, instead of consuming a buffer, a carbonic acid, your bicarb, you're actually producing bicarb as you shift that carbonic acid equation to the right. So that the bicarb, which is your carbonic acid buffer, doesn't really help buffer out the increase in hydrogen ions. Only your non-carbonic acid buffers do that, okay? When your non-carbonic acids are buffered, bicarb decreases, okay? Because the bicarb provides a buffering reaction. And so your buffer disappears as your hydrogen ion concentration goes up. If it's a carbonic acid that's buffered, carbon dioxide, then your bicarb actually increases, it doesn't decrease, okay? And this doesn't provide, this bicarb doesn't provide any buffering. It's left to your hemoglobin, okay? Which will sop up the produced hydrogen ions. When a change in respiratory function causes a pH change, the trajectory of that change is on a line with a slope of minus 11. I said 11, it's minus 11 actually, okay? So that means that when your pH goes up, your bicarb will drop, okay? Like this, okay? And that means, and when your pH goes down, your bicarb will be produced. That's assuming that hemoglobin is normal, okay? 15 per deciliter, okay? All right. That's all I've got. Thank you for your attention. I'm going to move on to video 3, where we will finish up by talking a little bit more about the anion gap.